So good afternoon, everyone. Well, it's a bunch. So work with in collaboration with a bunch of people. Especially Simon has not completely moved into machine learning yet. He's still doing some of this stuff. So don't worry, still there. But you know, there's this idea of type inference. So we want to check the correctness of our code, but we don't want to annotate everything with its type. This is very tiresome. So we invented this good idea of type inference, which essentially means, well, somebody will check the types, but it will actually figure out which are the types. And GHC, the Glasgow Haskell compiler, that's where we've been basing our work. That's a pretty good job in doing this, in inferring the types of your code. But the question is, does it actually handle every reasonable expression, where reasonable, of course, is with quotes, because that depends on everybody who is asked this question. So in particular, I would like to talk about the part where there is some instantiation, and that means that sometimes you have a polymorphic function, like head, which works from a list of every type to a value of that type. And the work of the compiler, in part, is to, once you apply the function head to a list which has a concrete type, like x's, which is a list of int, it has to figure out, well, you are applying head and you are substituting this a, this type variable, with the type int. So we also say that the type variable is instantiated to int. So what happens if instead of a list of integers, we have a list of polymorphic functions? For the time being, just for the sake of it, just for fun. So we just want to have this. So we could as easily say, well, if your list has for all b, b to b, and you apply the function head, well, you should just replace a with for all b, b to b, and that's everything you need to do. And this is actually what we call impredicative instantiation, because we change a type variable for a polymorphic type instead of a simple ground type. And this is actually disallowed by almost every practical compiler out there. In GHC, you have this flag, which is actually discouraged for you to use. So we didn't get there yet, and this is a problem. But just to give you an idea that this is actually useful, you will see that in many cases, people using ST in Haskell write this kind of code. So you have a function called $ or apply, which is just a way to apply a function to some arguments, and then a function like runST, which has this fancy type. So the type is not really that important. What is important is if you want to type check this code, runST $ and something else, which is something people write in practice, you need to instantiate the type variable a in the $ with the big type for all s, st, sv. So this is again an example of impredicative instantiation. And this is so common that actually GHC has a built-in rule which just looks, and if there is a $, it just says, I don't care, you know, this is like an application. So somebody had to write actually a hack in the compiler to accept this code. And one of the things we get in our system is that $ is no longer a special case. So this is something we can handle normally. So, I mean, we can actually not do this in general. So there is a theorem, I guess 20 years ago, which says that doing this in general is undecidable. And actually, if you try to do this in general for type inference, you very easily come to problems like this one. So one of the things is that there are no principal types. And if you take a function like single, which builds a list out of a single element, and you apply it to a function like ID, which is just the identity function, and you say single ID, well, you can wonder what actually you want to get in result. Do you want to get a list of polymorphic functions, or do you want to get a polymorphic list? In other words, where do you want to place the for alls? And the difficult thing here is that those types are not interchangeable, and one is not more general than the other. These are actually two different types, and you cannot turn one into the other easily. So this is something which makes this problem much harder than usual type inference. So what have people proposed in the past? So one way to do this is say, OK, I don't care. Just if you want to use these weird types, you have to annotate everything. So if you want to use head with your weird list, Just you have to tell me I'm using head in a weird way, and this is how you. So there is no inference, there is just checking. And well, checking is actually still undecidable, but at least we can do a better job. Another thing that people have thought about is, well, maybe our types are not as expressive as we need. So there is a huge strand of work starting with MLF, which says we can actually do type inference if you allow more complicated types. But the problem, of course, is that these types get more complicated. And suddenly, a function like this, which is just, well, it has two arguments and gives you the result of the second one, instead of being A to B to B, has this weird long type in the bottom, which says for all. AP, such as blah, blah, blah. So this is something which is undesirable. So the third idea is maybe we can restrict the set of programs that we can type check to a nice subset, and then, well, give a list of considerations to the programmer to know when his or her program will type check. And possibly we prefer this not to be, some obscure technicality in which essentially you end up saying, well, if your program is accepted by the compiler, then it's accepted, which is what you get in those cases. So really, there is a lot of work. People have been doing this for the last 15 years. And as I said, still no practical compiler includes impredicativity. So we want to do something about it. And our goal was actually to just get impredicativity in a way which is simple and is integrated in the whole ecosystem of Haskell and GHC. That means, first of all, that we want to get, as I said, a simple specification, so a simple way to know whether your program will type check or not, instead of just having to run it through the compiler and having to, scratch your head very hard if it doesn't. And actually, we want it to be compatible with the rest of the GHC extensions, which include things ranging from type classes and type families, JDTs, and higher rank polymorphism. So in some sense, we want just to extend the set of accepted programs, but still be able to type check everything which is out there. And actually, the second part is a novelty of our work, because most of the other works in impredicativity just deal with bare lambda calculus. So how do we do this? We took 3 key design choices. First of all, we had this notion of guarded arguments I will tell you about in a minute. We decided also to make every type constructor invariant. So yes, even functions are invariant in this system. And I will show you why this is not such a huge deal here. And the third thing we did is, okay, there is already work about how you can do type inference for GHC using this outside-in framework. Why not build upon it so we can get everything which already worked there? So let me show you, and as you can see, I didn't have enough time to write this in LaTeX, so I just did something which looks almost like LaTeX. It took me a lot to write the nice Ds. So anyway, imagine you just have head of IDs. So this is just a simple case, Head requires a list of A, and I have the type of IDs, which is list of for all BB to B. Okay. That's easy, just make the A equals to the for all BB to B. If my things are invariant, that's the only way that we can do it. So this really have to be the same. So just do it. And the key point here to notice is that the type variable A, in this case, appears in what we call a guarded position. That means that there is an argument in the application corresponding to that position in the type. So you have IDs, which will go into the list of A in the type of head. And also, the type variable A appears under a type constructor. So there is a list which somehow is guarding it from the outside and allows you to be able to do this impredicative polymorphism. So every time we have a variable like this A, which is guarded, and again, that means in a type, in an argument which somehow appears in the application and it appears under a type constructor, you are good to go. You can do impredicative instantiation. Now, if you have this case, single ID, in which the A appears without a type constructor there, we say, okay, in this case, we cannot give you impredicative instantiation. We have to restrict this case, and we force you to actually instantiate the ID from for all b to b to some beta to beta, and that means that the type of this whole expression will actually be for all b list of b to b. So we remove the problem before where we have to choose between two different options, and we actually tell you which is the one that you need to do. And this becomes a bit more subtle if you have several arguments. So imagine you have something like cons ID. In that case, you should only look as many positions in your type, in the type of cons, as arguments you have. So in that case, the ID appears in a position where you only have an A, so it's not guarded. So that means that in this case, cons ID, the A in the cons cannot be instantiated impredicatively. But now, if you give an additional argument, now you can do this because the A now appears under list of A. So you are now allowed to do impredicativity. And you can think about that in the second case, you can actually sort of look at the second argument. From the second argument, you can actually get the type for all A to A, so you know what is the instantiation, and then you can use this to type check the first argument. So there is like, this is the trick you are playing here all the time. And the second thing is that, as I said, all type constructors are invariant. So that means if you have a list of T, which should be an instance of list of S, the only way you can actually do this is by saying that T equals S. If you had covariance, you would be saying instead that T is an instance of S. And this is actually what restricts also the set of possible types for an expression to one only type. And also, as I said, functions are invariant. So no covariance, no contravariance. So this seems like a problem, but actually it's not so much in practice. First of all, if you have something like this, where F requires something which has for all AB and G has for all BA, this doesn't matter because the G will be instantiated and then regeneralized. So the order of these quantifiers doesn't really matter. If you have different pre-next forms like this, where you actually have a for all A and then an S set for all B, you can work around this by eta expanding the function. So you really have to do a bit of work to do this. And this was something that GHC used to do by default. Wow. But actually, this is not cool because it changes the laziness behavior of the code. OK. So after this incredible stage things, here is the cool theorem we got by doing all of this. So you know, if we have an environment and an expression, and you have if you can give two different types, there is actually a single type sigma and two substitutions. And well, you can just type check it with sigma, and you get that the other two types are just instantiation of this single type. But what is important here is actually the bold-faced thing, is that these substitutions are monomorphic. That means that it's more like Hindley-Milner style. So you can own the principal type you get. If you get list of A, this can be turned into list of int or list of bool, but it cannot be turned into list of something with a for all, which means that you have captured the whole polymorphism in your expression and given a type. And OK, you can still change some monomorphic components here and there, but the whole polymorphism is capturing the type you get. OK, so that's like the nice theorem. It's like a principal types theorem, but we weren't really sure it's a principal types theorem, so just call it you don't guess polymorphism. You don't get impredicativity. Now, as I said, we are building upon this outside-in type inference framework used by GHC. And the main idea of this is that instead of doing one syntax-directed go on your program, you divide type checking in two phases. First, you do constraint gathering, so you gather a bunch of equations that your types have to satisfy, and then you pass it to a constraint solver. And the first part cannot fail if everything is well scoped, and the second part is what gives you the type errors. And the nice thing about this outside-in is already can be parameterized by whatever constraint world you want. So in GHC, X would be like type classes and type families, and it already type checks GHCs and all kind of GADTs and all kind of extensions. But if you look at the source code in GHC, actually on top of this, there is a bidirectional process which is used to get higher rank information. And this is also something we wanted to remove. But anyway, the only thing we had to do is to extend outside in framework with 2 new constraints. So the first one says the type sigma can be instantiated to a function which has arguments phi1, phi2 to phi n, and a result mu. And actually, we proved that the result mu is actually always going to have a constructor in the top. And you also need a new type of constraint to tell you when you can generalize. So it's like the same thing, but with a slightly different less than or equal signs. And unfortunately, if you want to know more, read the paper. But well, I can give you a small example. So imagine you have something like cons of this identity function, 2 IDs. These are the 3 things you will get. You will say, okay, my function in the head, cons, has to have a type which has 2 arguments. So you have alpha1 and alpha2, and it returns a beta. Then my first argument has somehow to be generalized. If you want, this is a possibility generalization. It has to become an alpha1, and my second argument has to become an alpha2. So I have whatever experiment I have in the 2 arguments have to become what the function requires. And if you do this, well, you can just figure out actually by yourself what are the rules that you need to do. So if you find a for all, like in the first case, you just go and instantiate with new unification variables, and by doing this and remembering that everything is invariant here, you can just get from that alpha1 has to be equal to this unification variable delta, and alpha2 has to be a list of deltas. And then you can go and substitute this into the third case. And again, by having this invariance, you know that delta is for all dd to d. And by doing this, well, you can go into 2 and get the whole thing going. So you might think that, okay, this is because I just chose the right order to do all of this. But actually, we have a theorem which says that for every wall-type expression, you actually can always rewrite all these weird things to just equalities. So that means that you are back to square one. You are back to normal GHC stuff. And actually, if you combine this with a theorem from Potier and Remy, which is that you can always solve this set of equality constraints under for alls and existential quantifiers, you get completeness and principality, which is a nice result. So just to give you a clue of how we are implementing this, because otherwise I will get the question. So I made a prototype, which I just call it like my son, because they were born around the same age. So yeah, we actually sent this to PLDA 2015, and it took us a long time to get it working. We haven't implemented the whole thing in GHC yet, but we had a branch of GHC in which we enforce the invariants. So we don't use constraints to do the type checking, but we enforce all these invariants I've been talking about. And we try to compile a stackage, and almost all of it compiles, which actually means everything but one package. So I can actually point out the package, but that would be too bad from me. So anyway, in conclusion, what I presented here is a way to do impredicativity, which has a simple declarative specification, which is based on this idea of being guarded. So if you have an argument, and in the function type, the type of this argument appears under a type constructor, you are good to go. You can do impredicative instantiation. Otherwise, you cannot do this. You have to use old non-impredicative instantiation. We got it working with the rest of GXC extensions. So that means that you can get impredicativity with your GDTs and type classes and data kinds and all of that. And actually, by trying to compile all of GHC, we got a good expressiveness. Of course, this is not the final result, because we need to build in actually in GHC instead of having a branch which just imposes this invariance. But it gives us the confidence that we won't have to rewrite half of the packages in Hackage. We can actually make this work. So that's all. Thanks.
All right, we have time for questions. Please come to the microphone with questions.
So nice work. So I have one question. So what will happen if the same guarded type variable is compared to two different polymorphic types?
So that depends. So it might happen that, well, in principle, if you get to the case where you have list of something which is polymorphic and list of other something which is polymorphic,
yes,
these two things have to be equal. Otherwise, there is a type error. It might be the case that you can have one being a subtype of the other because of how you wrote the program. But in general, if they appear under a constructor and they are different, we just say that this is a type error, and you have to manually change something or it expand something here and there.
So it means there can only be one constraint that this type variable is compared to.
There could be different ones. So imagine you have instead of these cons, you have an append which has list of A to list of A to list of A. You can pass two lists, and you can have impredicative instantiation because this thing appears guarded, but the two lists need to have the same type. So you have to have the same things inside the list.
Okay, I see. And what if the variable is first compared to a monotype and then to a polymorphic type?
Then, I mean, that depends again. If they are compared with this instantiation thing, it could be that that's okay. But if you want to say that a polymorphic type is equal to a monomorphic type, this again is an error. So they really have to be equal, syntactically equal.
But I suppose the constraint you will generate is subtyping constraint, not equivalence constraint.
Yeah, that's why I meant that that depends where you are. So if you are in the subtyping thing, that's okay. You can say for all A to A is more general than int to int. That's perfectly okay. But once you get into equalities, then there is no way back. You really have to have syntactic equality.
Okay. Okay. Thank you. Yeah, I'm Nini from University of Hong Kong. Yeah, thank you.
Jan Hoffman, Carnegie Mellon. So you mentioned that this works with all the other extensions, or like a lot of other extensions of GHC. So how do you know that it works? Do you have a type soundness proof or something like that?
In the outsetting paper, there is a proof of the relevant theorems, and we have this theorem that in general we can always write this thing to a set of equalities. If you have more types of constraints, that means equalities plus any other types of constraints. So what we prove essentially is that you can get all of this in a first phase where you remove all the instantiation and generalization constraints, and then you go back to normal outside in. So that's where we get sort of the soundness proof from this.
So you mentioned you're making everything invariant. And I'm used to bidirectional checking often sort of imposing its own idea of subtyping based on this is more polymorphic than that. But you mentioned you are using bidirectional for handling higher rank stuff?
Yeah, no, so right now GHC uses bidirectional for higher rank stuff, and after doing this you don't need that anymore. So.
Oh really? Okay. I guess I will have to read the paper then.
Yeah.
I'm Justin Sleepak from Northeastern. Thanks.
So I'm Kathleen Fisher from Tufts University, and what has to happen for this to get off the branch and into GHC main? What are the gating conditions?
Oh, well, so the branch was just an experiment to impose this thing. So we are trying to build this thing, and when I say we, it's mostly a student and me helping. So it's just we're trying to get something working by the end of the year, but that really depends on how we have fun to make it work. So ideally, it's not that difficult, but it requires a lot of engineering. And once you build this into GHC, there is like a bunch of other things which you actually have to consider, like how you generate code for these things and how you simplify these kind of things, because if you just do naive translation from these constraints to system F, you get very large terms, and you want to simplify this so you don't lose some performance. So we still have to figure out those details.
All right, let's thank the speaker.